This screencast is going to show you how to solve Coulomb's law, finding the electric field using Coulomb's law for a surface charge distribution. The problem I have for you here shows the point P we're interested. This is the point P where we want to calculate the electric field due to this charge distribution here. So in this configuration, I have a charged cylinder, and the charge is only on the surface. So let's imagine that it's a hollow cylinder. You can think of it like a soda can, and all the charge is smeared on the cylindrical surface of the soda can. I'm not going to worry about how long it is. We could always put those into the limits of integration later. It could be infinite. It could be to minus L to L. We're just going to set it up generally so you can see how you would set up the R script, the R prime, and eventually the integration can just be done by the computer. I need to tell you about something, how the charge is smeared out over this first, and that will be sigma is our surface charge density, and that's going to be a constant in this case, just to keep it simple. I promise you we will do configurations where they're not constant. In our list of steps, what we had is in order to do problems like these, you should draw the picture first. So here's the picture. The next step we have is write down the formula. So the electric field from the origin, as a function of the position vector, this is from the origin to the point of interest P. It's going to be equal to 1 over 4 pi E naught. It's going to be the integral of the surface charge, which might be a function of R prime. In this case, we said it isn't. And now let's move over to our notation where we don't do R hat, script R hat over R squared, but rather R script vector over R cubed. That's just the same thing as our formula had before, and we did this trick for the line charge. Let's see if I can squeeze a dA in here. Yep, just barely. Our next step is to find the symmetry of the problem. This one should be pretty obvious. It's a cylinder, so we're going to use cylindrical coordinates. Let's define an axis right away. We can do a z-axis here. We know that what we can do is what we're doing is drawing Cartesian axes, even though we're going to be in different systems. So this still could be the y-axis, and this could be the x-axis. I'm going to leave it unlabeled. There's not really an s-axis. Remember, s is the radius that Griffiths uses for cylindrical coordinates. We're going to use s, but I gave you a handout in class that uses rho. Many people use rho for cylindrical coordinates. Okay, so we have cylindrical symmetry. That's what we've decided. Let's actually define some of the parameters now, like R script and dA and R script vector, and write these in terms of the cylindrical vectors and unit vectors. So first let's start with dA. We need to think where we're integrating. We are integrating on the surface of the cylinder, so A is constant. So we're not going to integrate over a ds. So A, the radius, is constant, so no need to integrate over ds. We are going to go around this, right? So we're going to go 2 pi around, and then we're going to take little rings of z. So the dA for this problem is going to be equal to A d phi. I'm going to prime it. That tells us that we're we're integrating over the charge distribution dz. Okay, great. Now what you may have seen here, I didn't label this before. This is just my area element. That's supposed to be my little area element on my cylindrical surface. So let's go on to R vector and also get the R script vector, that is, and then the magnitude of R script vector. So recall that our vector is going to be, let's use our colors again. We started with blue, if I recall. Position vector minus the vector to the charge distribution. And then let's draw those on our picture. That's actually our next step, is to define R script. So we drew the picture, we wrote down the formula, we determined the symmetry, and now we're on step 4. That's determining the R script vector. All right, what do we want to do first? Let's do the blue. Let's go from the origin to the point of interest. So even though the point of interest happens to be on the y-axis here, we can even assume, in this problem I'm going to assume that was just coincidence. All right, so we're going to keep it general when we write our detailed vector. All right, let's draw. There we go, and we're going to call that R. Let's do our R prime. That goes from the origin to the, in this case, the charge distribution is everywhere on the cylinder, but we're going to just do one element of area at a time. So I'm going to draw this to my area element. That's going to be R prime. And in fact, why don't I label that dA? That little area element dA. And now what we have left, in fact, this is, we could have done this first. Remember, we're interested in how, if I put a point charge here, how it would move, a positive charge, how it would move because of this area element here. That's going to tell me which way our script is going. So it's going from the source here to the point. All right, and that's going to be our script. Very good. I'm going to go to a new screen because I'm out of room here, and let's define R prime and regular R position and R script in more detail. But before we do that, I noticed one small mistake. Let's make sure we're integrating over the charge distribution in Z. Great. Okay, on to the next screen and definitions of R and R prime in more detail. All right, here's a clean screen. And let's define the position vector and the R prime vector in more detail. Let's start with the position vector. Going to be equal to s hat. So the vector here, s hat, that actually could be any vector drawn from the origin to a point in the xy plane. Remember, a generic point in cylindrical coordinates would be s hat plus z hat. All right, and so all we've done is we've restrict a point to the xy plane. What we will do in this problem is we are going to assume it's along the y-axis in the end, because otherwise the problem gets really, really nasty. And something I can do right now, even though we're in cylindrical coordinates, often in E&M books, we still will call this x and this y, even though we're going to integrate in cylindrical coordinates and do everything in cylindrical coordinates. Well, almost. We'll convert. So basically, when it is time to call phi something, phi is going to be the angle from the x to the y-axis, okay? Now, if you're integrating, if it's on the charge distribution, that's going to be a phi prime. If it is in regards to your point in question, it's going to be just regular phi. All right, stay with me. So I'm going to give you the real deal here. The book skips over this. All my books don't ever do these kinds of problems in their nasty glory. We're going to do them sort of in their nasty glory because I think they really gloss over some key detail on how to set these things up. All right, on to R prime. This one it's not a generic point in cylindrical coordinates because we're restricted on the surface of the cylinder, so that's going to be a s hat prime. Okay, notice the difference. Plus z prime z hat. All right, and now for our script R. Our total vector is going to be s hat. Let me erase that and make that look more like an S. Still learning how to use this stylus. This is the state-of-the-art stylus for an iPad, and it is still not fantastic. Or maybe I'm not fantastic. That could be actually the real problem. All right, SS prime minus... Oh, come on again. All right, one more time. Minus, can I get an A? Not too bad. S hat prime minus Z prime Z hat. All right, and you might say, well, why didn't you prime this this Z here? We can if we want to. If you actually, again, somebody asked today in class, what happens? Can I prime this? Over priming actually isn't a terrible thing. The thing is, the reason we prime is in the end we need to convert the primed unit vectors in curvilinear coordinates to x, y, and z. So in the end, because those curvilinear unit vectors depend on things like theta and phi, which we're integrating over, actually we're integrating over theta and phi prime, not theta and phi, which might also be in the problem. We only really need to keep track of primes in the curvilinear and not in Cartesian. And if that doesn't make sense, hopefully you'll see what that means in just a little bit. All right, here's something that, in a sense, it might break the order of our steps a little bit. We need to find the magnitude of our script, in order to correctly find the magnitude, we should really convert that R script into Cartesian coordinates right now before putting everything in the integral. So let's do that right now, and this is going to look really nasty. So let's do it all in green. And first of all, what we need to do is we need to find out what S hat and S hat prime are. So S hat, this is in your handout, and it's also in Griffiths as well. S hat is going to be cos phi x hat plus sine phi y hat. And we're going to draw that in class just from geometry, which actually I think is rather fun. S prime hat, guess what? It's going to be cos phi prime x hat plus sine phi prime y hat. Great. So now let's convert everything into Cartesian components. And this is really to get the magnitude. We can leave everything in Cartesian from here out. You'll see in this problem it actually makes sense to convert back into the S hat direction, just because we don't integrate over it. So I'm going to, hopefully we'll get the rules straight here. If you're not integrating over it, you can leave it alone. If you're integrating over it, you have to be careful. All right? So our script then is going to be S cos phi unprimed minus A cos phi primed. That's the X component. The Y component, I'm going to run out of room here, is going to be similarly S sine phi. Now I want to move it over to the left. I think unfortunately they're all connected. Let's see what happens. Yeah, why don't we do that anyway? All right, I'm going to move my drawing too. Let's just get that cylinder out of there for now. It's a beautiful cylinder, but we'll bring it back. Nope. Almost here, bear with me. All right. We know the cylinder's there. All right, I'm even going to move this maybe off the page. Let's get our script on the page. There we go. We still might not have enough room. Okay, where were we? Minus, get my pen back. A sine phi prime y hat ick, and then, oh thank goodness the last component is easy, minus z prime z hat. Alright, let's copy this over to the next page, and then what we're going to do, guess what you're going to do if you want to find the magnitude? Let's square each component and square root it. Okay, so let's get the magnitude of this R script vector. So the magnitude R is just going to equal those components squared, square rooted. Let me draw a long radical. All right. See if I can try to write neat here. It's going to be S cos phi minus A cos phi prime squared plus S sine phi minus A sine phi prime squared. Oh, we're running out of radical. Plus, that's still under the radical. What's going to be down here? And of course, it's just my little z prime component. Plus z prime squared. This is the nasty full glory way to do it. Let's simplify it just so we don't do a lot of algebra on the screen that you can do on your paper, and then you don't have to watch me with this blunt instrument try to write neatly electronically. So let's do this. Let's assume how the cylinder was drawn is our position vector was actually on the y-axis, and let's do that. And so all that entails is let's make Oh, that's my laser pointer. Let's make phi, not phi prime, right? Phi prime we're going to integrate over. Let's make phi equal to 90 degrees. Okay, and so that's going to help us out quite a bit here. Anytime there's a cos phi now, these are going to go to 0. 0. These are going to go to, this one will go to 1 here. This one is going to go to 0. This one is going to go to 1. And I think that's it. Okay? So let's rewrite this now a little bit nicer. Okay, so I might run out of room here again. We'll write it general, and then we'll probably have to use another screen. Actually, let me tap all of this. It should all move together. That's kind of funny, most of it. All right, and then if I tap, hopefully I'll be able to separate my equations. All right, so our vector in this case is going to be equal to minus a, oh, come on you, cos phi prime Oh, bear with me here. All right, I'm trying to speed this up because I think these other screencasts have been a little bit slow. Okay, there we go. And then I can't forget my s, so I'm going to have on my y component. So plus quantity, it's going to be s minus a sine phi. Come on, you. Prime. Okay, that's the y component. Did we get it? I think we got it just fine. Minus z prime z hat. Cool. Let's see if we can squeeze in the magnitude. Let's see if this one moves by itself. Good. All right, that one moves by itself. And let's try to get the magnitude of this now. So our magnitude is just going to be the square root of each of those components. Those are going to be a little bit easier to deal with. All right, so the first one, you'll see there'll be some simplification. We'll simplify in the next screen. I'm going to get an a squared cos phi prime squared plus a quantity s minus a sine phi prime squared plus z prime squared. Now you'll see that we're going to get a cross term because of this this quantity inside the parenthesis, and that actually means something pretty meaningful if we think about how the integral is taking into account all the vectors as it's sweeping these rings of the cylinder, or these little area elements across the cylinder. So even though this looks ugly, I like it, and hopefully you'll like it too. And the problems you'll be doing in the book, and the problems I'll assign you are not going to be this bad. But I want you to know the general way to go about it, because you might have test problems or other homework problems where you just set it up. You don't have to do it, but at least you have to set it up in the most general possible way. In real life, you would set something nasty up like this, feed it into a computer, and let the computer chug on it. But if you don't know how to set it up, obviously you can only do book problems, and we want to do real life problems. Okay, let's do just a little algebra together, because I think it's worth chugging this all the way through. And this is even simplified a little bit. Remember, we're restricting to theta equals 90, not theta, sorry, phi equals 90. Think of if we left all those other phis in. All right, so let's do this first. So we have a squared, this is just inside, cos phi prime squared. And now from the other term here, right, I'm getting a squared sine phi squared prime squared, and that's actually going to simplify. So this is all under a radical. I'll draw that radical at the end. I'm just going to take one term from the term in parentheses, a squared, oh, come on, n, sine phi squared. All right. So right, I did the first term and I'm working on here. I just took the plus. You'll see why I put it in this order. S squared, and then plus that cross term, which is going to be minus 2as sine phi prime squared. Ooh, we can just squeeze in the z prime squared maybe. Let's see here. Let's move this whole thing over. Oh, come on, one at a time. All right, that's all right. We can live with that. Plus z prime squared. And let's put that all under the radical. Okay, check it out. The reason I did this term here, when I group them, that's just going to be a squared, right? Because cos phi squared plus sine phi squared is going to be 1. All right, so that's going to be a squared, again, plus s squared minus 2as sine phi prime plus z prime squared. That whole thing's under the radical. Okay, so let's see if I can squeeze that in. Well, let's just we'll just rewrite that below. So equals a squared plus s squared plus z prime squared minus 2as sine phi prime. Cool. All right, we're going to shove this into the formula, and then once again, I won't forget, I want to talk a little bit about this at the end, how that's actually keeping track of all these important distances. This is the final expression up top here. This is our final expression for E field given all the other work of finding R script, R magnitude, or sorry, R script magnitude, R script vector. So R script vector is just on top. Sigma comes out because in this case the surface charge density is constant. The a squared s squared z prime squared minus 2a sine phi prime squared to the 1/2 is actually the magnitude of the vector up here, and then we cube it because in the case that I'm writing here, cubing is the Coulomb's law of dependence if I have R script vector up here rather than R hat. So really, right, this is going to be R script vector over magnitude and then divided by the magnitude again. This is why we get the cubed. Where I'm integrating is I'm integrating over this shell down here, this cylindrical shell. So A is constant, but I need to integrate in a ring, d phi prime, and then I'm going to take those rings and add them up one at a time, those bits of charge, those rings of charge, and that'll be z prime. What I wanted to note, there's something that I think it's a little tricky if you're not paying attention, is where this came from. You might be inclined to just get a squared, s squared, z prime squared. But this term is very important here. So if you imagine my patch of area, and this is going to be, you're going to have to use your imagination because we don't have 3D screencast space. In the future, we'll wear glasses and this thing will pop out at you. But right now, let's shove in some values for phi prime. Right, so we'll pretend we're integrating. This dA, right, is going to change. It's going to change over here, over here, over here, which is going to change where this vector sweeps out, which is going to change the distance of R script, right? And down here, this is just the distance of R script. So imagine, if you will, that phi prime, phi starts from the x-axis, that's x, that's y. Phi is going to go, if we go all the way to the y-axis, that means phi prime, this is for the integration variables, phi prime is 90. So if phi prime is 90, that means that this triangle here would actually be in the YZ plane. Let's actually label that, right? So if phi prime is 90, all right, if phi prime is 90, then this triangle here is actually restricted to the YZ plane. All right, and then that distance, my claim, is actually going to be the shortest. It's going to be the shortest R script vector. Because check it out, if this is in fact restricted to the YZ plane, and that means that phi prime is 90. That means that sine phi is 1. So you get all of this distance a squared s squared minus z prime squared minus 2as. All right, contrast that with a different part when we're going to integrate we're going to take all these bits of area, bits, all along this cylindrical surface. And when we get to the bit of area that's way over here, imagine now that we are in the negative yz plane. So at some point of the integration, the r prime vector is going to be way over here, and therefore my r script vector is going to be longer. Okay, and again, imagine, if you will, that for the little charge element that I'm integrating at this time, a part of the integration, I'm in the negative yz plane. So actually, phi is 270 degrees. And so if I plug that in, that's going to be a -1. That's going to make this positive down on the bottom. So I'm going to get the a squared plus s squared plus c prime squared plus some extra stuff, right? And we can see that this thing is physically longer here. All right, so in the original case that I set up, I had a patch of area, and we couldn't tell what phi prime was, right? Phi prime is going to be everything, because we're gonna go 0 to 2 pi, and then we're going to shift up in z, and then 0 to 2 pi. But in the instance, we're just pretending at one instance where the element is such that we're in the yz plane, I'm going to get this r script vector, and it's going to be this length. At another instance during the integration, when I'm over here in the negative yz plane, I'm going to get this longer vector. So what I'm trying to say basically is down here, as we would expect, right, wherever the integral is integrating, we keep track of the length down here. Just wanted to emphasize this because this part could be sneaky. And of course this part up here keeps track of the direction. Again, your book problems are not going to be nearly as nasty. And then note that we actually made ours quasi-nasty because we restricted our point P to actually be along the y-axis, right? This point P could have been out here, or it could have been out somewhere in space where phi wasn't 90. So this quasi-easy problem is still nasty, and you get to do these easier ones, and pretty soon we'll move on to Gauss's law, where we're going to totally avoid this altogether. And in real life, you might not be able to avoid it. You'll have to set it up nasty and plug it into the computer. As I'm looking at this final expression over above, I noticed one small mistake. You might have caught it yourself. There should be an A in front of the sign right there. I'll see if I can squeeze it in. Or maybe just put a caret. A. Okay, so there should be an A right in front of there. Now we're fine.